No worries, team. All right, ladies and gentlemen, small group today, but maybe we'll get a little bit bigger as we go. Okay, so Carl started throwing some definitions around the chat window. Thank you very much. But today we're going to talk about how to use fault trees to conduct root cause analysis. And don't worry, Carl, we'll go through what a fault tree is as well. Now, before we really hook into fault trees, let's get on top of what root cause analysis is, because root cause analysis is something which seems very trivially obvious when you read the title of the activity, but many RCAs, as we sometimes say them, actually furiously solve the wrong problem or furiously admire a problem. And we're not about admiring a problem, we're all about trying to improve things. And that usually starts with, from a reliability perspective, understanding why things fail. If you understand why things fail, that's one key step for RCA. But the next step we need to go through is then ask ourselves, what can we do to stop things failing? And once we answer that question and then implement the answers to that question, then we can say that root cause analysis is complete. But before we even think about root cause analysis, let's talk about what a root cause is. Now, a root cause is a very controversial topic. It shouldn't be. But the reason why it is controversial is that the definition that you often see in textbooks like this one, root cause is the initiating cause of failure, is very subjective. What causes failure? Is it the public school system? Is it the meteorite? Is it our customers using our things in ways we didn't anticipate, etc., etc., etc.? All those things are technically true, but you can easily skew your perspective to settle on the answer to the question that best suits your calendar, your work schedule, your work-life balance. And the reason why is because the actual root cause for you is based on the thing that you/we can change to make sure that failure hardly happens again. So as a rule, a root cause is something we did not do, a human behavior. That's the only thing we can change. So let's look at what I'm talking about by going back to good old faithful smart lock and try to find the root causes of failure of the smart lock. And some of the veterans of my webinars over the years, this will be a bit of revision, but a smart lock's a wonderful combination of modern smart technology combined with traditional mechanical lock technology. And of course, when things go wrong with our smart lock, whether it be in the hand of our customer, a user, or if we wind the clock back to our production, maybe it's not passing a test, or maybe a prototype isn't doing what it's supposed to do. We then want to know why the failure has occurred so we can do something about it. And if we are lucky enough to be able to pull our smart lock apart such that perhaps it is a test that was conducted during production, we can actually eyeball and look at specific components, specific subsystems of our smart lock in a way that we cannot easily do if this same smart lock fails in the hands of a user or customer. Now, if we zoom in even more, perhaps the most important element of our smart lock's very subjective call again is the electric motor, which turns the gears in the gear set that then essentially drive the bolt in and out of the striker plate on the door. And of course, all this is controlled by the printable circuit board, which provides the current and voltage to make the electric motor turn. So you be my guest when it comes to signing them, working out which one of these three is the most important component. In many cases, it's not necessarily super important to delineate between these three components in terms of their relative importance, but they're all very, very central to what our smart lock is supposed to do. And let's just say that during our test that we conducted on our smart lock before it was released or deemed ready by the final design review board, when it didn't work during test, we pulled it apart and we identified that there were solder joint fractures at the cables connecting the electric motor to the PCB. Now, what could a root cause for this failure be? Remember, is the solder joint fracture itself? Is that the root cause? Now, many organizations would say the root cause of failure is solder joint fracture. But Can we change that? Can we change that solder joint fracture to make sure this failure doesn't happen again? We can resolder the joints, but there's a pretty good chance that if we resolder, as in actually repair those fractures, that the underlying reasons that cause those solder joints to fracture in the first place will re-emerge sooner rather than later. So the solder joint fracture of itself is not and never will be a root cause. The root cause is whatever is a bunch of different factors, perhaps, that led to this solder joint fracturing in the first place. So let's ask ourselves another question. Perhaps when this test was being conducted, it was a test which is a robustness test where perhaps this smart lock was installed on a door to simulate customers slamming the door very hard. And when they were conducting the serial of the test where the door slams were enacted, that's when the solder joints fractured. The door slams root causes. Well, can we change door slams? Can we stop our users from slamming doors? Now, you might look at the test itself and say, and perhaps in reviewing the test, you realize that the test was exerting forces that far exceeded what you'd typically expect for a door slamming event. If that's the case, that's fine. Then you might have a test exception. However, if the test itself generally replicates the forces and stresses that a smart lock will experience during a door slam, and we believe that there will be times where the customers and users will slam the door, or the door is left open and a gust of wind comes through the house of the building and slams the door. If we believe door slams are part and parcel of how our customers and users should be using our door, remembering you don't want to be that smart lock manufacturer which has a huge disclaimer on the packaging, something along the lines of, warning, this lock will fail if the door is slammed. That's not a really strong endorsement for quality, robustness, and reliability. So if we believe that our customers and users will, well, enough of them at least, will routinely slam doors, and we don't think we can change that behavior, then the door slams are not a root cause. Now, I want to emphasize this part because a number of root cause analyses I've seen where the customer or user is blamed, customer abuse, customer misuse, etc., etc., etc. And that essentially assigns that root cause to the scrap heap of critical thinking. It's that number of scenarios where I've seen that is beyond startling. It's just a get out of jail free card. And as a rule, customers and users aren't trying to ruin your day. Now, let's keep going on this discussion about what root causes are and what root causes are not. Perhaps if we look a little bit further, the solder joint fractured during testing, and we concluded that door slams in the testing serial was otherwise fine and okay, then maybe we ask ourselves, are these solder joints designed in a way where what we're asking of them during the door slamming events is something beyond what they're designed to do? Solder, its primary function of solder is to conduct electricity. And yes, it is there to secure cables and secure wires and the like, but it is not the strongest bonding material, and we all know that. And so we need to be very careful about what we ask our solder joints to do. And when in a door slamming event where you have a lot of momentum accumulated by those cables connecting the electric motor and the PCB, and those cables are essentially flailing wild and carefree within the chassis of our smart lock, only thing restraining those cables are our solder joints. Maybe if we ask ourselves did we ask our solder joints to do something they weren't supposed to do during a design process, such as create a design which is incapable of tolerating shock loads and cable connections? Now we're onto something. Now we have a root cause we can do something about. Now we have a root cause that is allowing us to make things better moving forward. And that means we can come up with a bunch of really great ideas, including things like these ones, where we have thicker gauge wires to provide more contact area with the motor terminal. We have shorter wire to accumulate less momentum. And we have wires that are clipped to physically secure them. And what that means is that the shock forces are not are not going to be exerted through the solder joints. They're going to be exerted to the very strong chassis or frame of the smart lock. At the PCB, we now no longer have solder joints. We have sockets and plugs, which are structurally much stronger, and they have the additional benefit of being able to be easier to install and assemble. Another thing we can come up with is visual inspections of motor solder joints for and have that added to the supplier inspection checklist, because we know soldering defects, manufacturing defects can lead to weak solder joints. And maybe, if we're really concerned about it, we can have surveillance automated microscopic optical inspection for the 10% of incoming motors. And that sort of inspection allows us to identify if there's any substantial changes in the inevitable number of defects that there will always be in solder joints. And if we are able to see those defects starting to creep up before a problem is caused, maybe we can speak with our supplier and see what's going on. Now, I can see, Carl, you're furiously typing away lots of Q&As and lots of links and things like that. I'm going to do my best, but I'm not going to be able to go to the links that you are typing in during this webinar. So I'll see what we can do, but I'll have to throw some realism on some of these questions and answers and comments. I'll get back to as many as I can when the right time comes up. Now, when it comes to RCA, is this little explanation I went through perhaps too simple? What do I mean by too simple? Let's look at this. We'll go back to our smart lock, for example. And what happens if we don't have the ability to get on top of the actual physical failure mode, the fractured solder joints? Now, for example, this might be a scenario where our smart lock has been successfully launched, so to speak, and now we're getting a ton of warranty claims. Our users and customers are saying, hey, this thing's not working the way it should be. And as a rule, you cannot guarantee that you only get your smart locks back from customers and users, because they're the ones who are going to who are already frustrated with the lack of support or service that they're getting from our smart lock, and they're not necessarily inclined to help us out. They just want to be replaced or repaired or have the problem go away. We might not even get a detailed description of what happened. Again, especially if this failure event caused a significant distress or inconvenience to our customers. Yeah, good luck getting some of the information back the way we could if we were testing these things ourselves, able to pull the smart lock apart and visually inspect the components. So we just might know that our smart lock is failing, but not have a really good idea of what's causing the failures from a very physical understanding of what's going on. And that leads us to root cause analysis, which, yes, can be associated with a simple inspection of a failed smart lock under testing conditions, where we can pull it apart so the solder joint's fractured, which allows us to more easily find the true root causes of failure. Now, many root cause analyses need to be conducted with precious little information. We need to use this amazing thing called our brains to speculate in a constructive way about what might have caused that particular failure to occur. And then once we have a myriad of ideas, we then prioritize which ones are the most likely ones that we then inspect further. And if you've ever done RCA before, you might have heard of all these different acronyms and ideas that you can see on the screen right now: the 8Ds, the 5Is, the 5Ws, 1Hs, 6Ms, Pareto analysis, FMEAs, SPC, FTA, Shikawa diagrams, DMAIC, Apollo, etc., etc., etc. So what we're going to do right now, as opposed to go through a detailed description of each one of these things, where at best you can only memorize what each letter means, let's go through what the principle of root cause analysis is all about. Because sometimes textbooks and people who have certain colored belts, all they teach you is just the mechanics of how you go through root cause analysis, and not so much the dynamics, because it's very easy to be a master of the stuff in the books, but not actually find the true root cause, especially if you're looking at this definition of root cause, remembering that a root cause, if you're serious about root cause analysis, it's a thing that we can change to make sure that failure happens hardly happens again, which means the root cause by definition is something you own. If it's something you don't own, then that's not a root cause, that's an environmental consideration. I'm going to look at that in a minute. I'm going to start using some visualization to help us explain the idea of root cause analysis and what a root cause is. I'm going to use this apple here to represent a failure event. In this case, the apple is going to be growing on a tree, the tree of failure. Yeah, this is a bit of revision for some of the veterans. When we have this tree of failure, which is a useful visual because a root cause, the term root obviously comes from the language of plants, the thing that goes underground that makes these plants be successful and grow happily. Now, on our tree of failure, you're going to have lots of different apples representing different types of failure. And some apples will be much bigger or more expensive or more critical or more severe than other apples. And so those apples should be big, red, and angry. You can see that we have a very severe failure, that big, red, angry apple at the top. And that also means that one of these smaller apples over here, it's a minor failure. For whatever reason, it's not quite as big a deal. Maybe it doesn't happen nearly as often. Or maybe when it does happen, it's not that big a deal. Now, if you make every failure important, then no failures are important. So you always need to understand the vital few apples which are ruining your day more than most others. And so that's one of the first things when it comes to root cause analysis. You don't want to be a lawyer. A lawyer mindset is all about definitions and binary classifications of something being a root cause or not. No, you need to be a lot more nuanced than that, and that's where us engineers can sometimes struggle. So here is our tree of failure, all these apples. Now, the one thing you can do to mitigate failures is essentially get rid of our tree of failure. This is analogous to a repair where those failures are immediately made to go away. We call whatever that is the immediate action, something we do to rectify the initial consequences of failure. So corrective maintenance, recall, repair, containment, isolation. Now, the problem with the immediate action is, yes, it does have an immediate effect, but plants have this really, really interesting characteristic where they simply grow back, especially if their roots are intact. So when it comes to root cause analysis, we need to find those root causes, and attack those roots. And those root causes are dirty, they're beneath the ground, and often embarrassing because it's all about decisions we did or didn't make. And so when it comes to root causes, of course, there are usually lots of different ones which contribute to a failure event. And as opposed to making things more complicated, this is actually a really useful characteristic, because then you can perhaps pick and choose which root causes you want to tackle or leave aside. So remember, root causes have to be something you can do something about. So, for example, a supply design or manufacturing error is not root cause, because that statement by itself is all about telling people who was at fault. That's all about blame / avoiding responsibility. I've seen many root causes go as far as that, no more. So this is not a root cause, even though you might feel like it is a root cause when one of your suppliers lets you down and gives you a batch of defective parts or defective components. If you arrive at this as a root cause, at best, you can get angry and send frustrated emails, but that's not going to necessarily make things better moving forward. What you need to think of is the more humble ideas, like, did we not establish a collaborative reliability strategy with the supplier? Did we give them the incorrect specifications to the supplier? Are those specifications technically okay, but sort of very close to being defective, so to speak? So any failure, any deviation, even close to these specifications, could precipitate failure. Is there too much time pressure placed on the supplier? If you're thinking about these sorts of questions, this is not about a new age lovey-dovey tree-hugging approach to the world. This is all about what you can focus on to improve quality and reliability. So these are things that you can deal with, you can address. You can yell at the supplier, or you can look at what did we do wrong with the supplier process. Maybe you selected the wrong supplier because you went with the cheapest, nastiest supplier. That happens a lot. Not the supplier's fault when you do that, because if you go for the cheapest, nastiest supplier, where even the most rudimentary analysis would realize that they have to make a loss to give you components at the quality that your contract demands, that's on you. And so root causes are all things that you can change, and perhaps things that are embarrassing if you look back in hindsight. Not necessarily the initiating cause of failure. They are the things that we can change to make sure that failure hardly happens again. So by definition, it's a human behavior or a decision. That's the thing you can change. You cannot change a physical phenomenon. You cannot outlaw corrosion, for example. That's a physical process based on the laws of physics. You cannot outlaw the laws of physics, so to speak. Corrosion has been and will always be a physical phenomenon, for example, that you cannot eradicate as a concept, as a phenomenon. But what you can do is make decisions which eliminate the conditions that allow corrosion, for example, to ruin the day of your product or system. Now, when it comes to root cause analysis, we often hear about this thing called failure analysis. Now, failure analysis is all about finding out how something fails, where root cause analysis is finding out why something fails. So you might send off your failed solder joints to a laboratory for them to do some really intrusive, maybe electron microscopic inspection, et cetera, et cetera, et cetera. And they'll give you a report, comes back and says, yes, we found this void here, we found this over here, and we had evidence of solder fatigue over here, et cetera, et cetera, et cetera. That's failure analysis. Root cause analysis is all about taking that information and learning what you need to do about it to make sure that that failure hardly happens again. So failure analysis is very important, but it's not root cause analysis. And many root cause analyses require failure analyses, not all, some do. Now, when it comes to root cause analysis, a topic which gets brushed over a lot is the topic that I like to, or the concept I like to refer to as layers. So if we look at our failure event, a big red angry apple at the top, when we, for example, have a bunch of feedback from the field, from our customers or users saying, hey, these smart locks, they're failing in our warranty period. We're paying lots of warranty costs as a result. That's a pretty big red angry apple when you have to pay a lot of warranty action, pay for a lot of warranty actions. Well, if that's all the information you have, then at best, you can think of a bunch of causal explanations as to why that occurred. And you're about to see that represented on the screen right now. What you're seeing are causal chains. And these causal chains just represent different events or categories of events where, depending on how each one of them starts, they could result in your failure event. So remember, at this stage, all we know is our smart lock is failing during the warranty period. Without anything else, we might be able to, if we were to genuinely squeeze every last drop of information out of our collective intelligence back at the manufacturing facility with all the experience and the expertise from our staff, we might be able to, at least in principle, construct something which looks a little bit like this, where we have all these different causal chains which could explain why our thing failed. Now, this is very important because root cause analysis is not all about rushing to your favorite root cause, which is something that some methodologies like 5 whys almost demand. Now, when it comes to root cause, you can see these causal chains have at the bottom these red bulbs. These are the root causes, potential root causes for our failure event, our warranty failures. And I think we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 potential root causes for this scenario where our smart lock's failing in the warranty period, and we're not entirely sure which one or which ones are causing the failure. But at this stage, this is all we know, or we could know, or that represents the extent of our knowledge. And so each one of these little chains is, like I said, a single causal chain, a single description of a scenario which might have led to our smart lock failing during the warranty period. And that essentially means we have a root cause which triggers another event, which triggers another event, which in turn triggers another event and another event, and this one, and then this one. And finally, that event, which then is the last thing which causes our smart lock to fail. And so root cause analysis is often going through the causal chain to try and get to a potential root cause. And then causal chains can interact. So for example, you might have two root causes which could trigger this causal chain. And it also means that if you have both root causes present, it might trigger that causal chain really quickly. Or maybe this causal chain needs to have a root cause from another causal chain concurrently in the design of our device, because without those two things occurring, then then the causal chain cannot propagate up towards our top event, and that is a really, 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 really useful characteristic, because then we only need to stop one causal chain. Now, that leads us to the concept of a corrective action, because once we have a root cause, something we did or didn't do understood, then the corrective actions become really easy to find. And sometimes corrective actions, which are also called fixes, are an action that involves a change to a system design, operation, maintenance procedure, or the manufacturing process of the said item for the purpose of improving its reliability. And so we're going to use this little illustration, this little logo, this icon to represent corrective actions. Now, things are going to get a little bit busy on the screen because of those 19 potential root causes. We haven't identified which ones are the true ones, so to speak. There will be, as a rule, more than one corrective action for each potential root cause. Why is that? Just because of physics. So you might have a bunch of different ideas which will be able to explain why you're able to prevent things from occurring. Now, you can see here for example, on the root cause on the sort of halfway up on the left, there are 3 green check marks. There's 3 icons, corrective action icons, which we can choose to address that root cause. And so, if we look at, my computer decides to keep up. Each one of these potential corrective actions, we might be able to identify which ones are way more expensive or way harder to implement. You can see what some money bags trying to represent or help us see which ones are way more expensive than the others. And of course, that often leads us to identify those really fast, simple, free corrective actions that don't incur much time, don't incur much change to our design, and are effectively free because they are able to essentially involve a change in our design as opposed to complete reworking. Remember those 6 corrective actions we looked at at the start of this lesson for those solder joint fractures? I think we had shorter cables, thicker cables, and what else do we have? We had those cable clips. Now, technically, those clips aren't free, but they're so inexpensive compared to the overall manufacturing or production cost of the smart lock that that they would be effectively free from a decision-making perspective. And these are the corrective actions that you're able to implement really early in design. So if you are concerned about these solder joints to the extent they might appear in a familiar, which is something you typically do very, very early. So you design your smart lock in a way where solder joint fracture is already unlikely to occur because those corrective actions have already been implemented in your first design. Then they are those fast, simple, free corrective actions that allow you to quickly build robustness and reliability without having to reinvent the wheel or conduct rework or have those really expensive redesigns later on in the production process. Because once you design everything else of your smart lock, it's very hard to implement these fast, simple, free corrective actions. So these are the things that you want to identify really early in the design process through familiars or halt. And so that essentially they mean that these warranty failures will be unlikely to occur and you haven't paid a lot of time or money for that privilege. So there's those fast, simple, free corrective actions which often disappear once once you are progressing through more detailed design. So, for example, an example of a corrective action which is fast, simple, and free for a non-smart lock application would be mounting a PCB on the left side of the engine bay away from the hot exhaust manifold on the right. PCBs don't like heat, so if you can just simply install a PCB within your system which is away from sources of heat, you have potentially saved the day. Perhaps when it comes to manufacturing, you're going to use an automated mixer to ensure correct amount of vulcanizing agent in your silicone rubber molds. And yes, an automated mixer does come with a cost, but they're relatively inexpensive compared to having to re-engineer or put that automated mixer in later on. Sometimes you can, sometimes you can't. Another example, oh, go back, is to have color coding wires in a wire harness. Why is that a fast, simple, free corrective action? I have seen, especially military vehicles, where every cable is white. And so the poor old vehicle electrician, or whatever the correct term is, when they're trying to conduct repairs, it's borderline impossible for them to really be on top of which cable or which wire needs to connect to which other cable or wire, because they're all white. If they're simply color coded, it makes everything very easy, which is a fast, simple, free corrective action that you can put in your first design, but you certainly can't do it later on. Maybe another example, oh, we've gone back, my bad. Another example is conduct finite element analysis on the door handle to ensure all stresses are below the endurance limit of the steel, so fatigue can never happen. That might be a simple thing where we just change the inner radius, something very, very simple. And that means without much cost, if any, fatigue will never happen. So that's what we're looking for when it comes to root cause analysis. Make those fast, simple, free corrective actions, especially if you identify them very, very early. Now you can see on this diagram here, we have interactions between causal chains. Like I said, they're very, very helpful because that means that implementing these corrective actions, those two fast, simple, free corrective actions over here on the far left-hand side, either slow down the effects of the other causal chains or eliminate them entirely. Essentially, stop those causal chains from causing failure, because perhaps those causal chains need that root cause that we have now addressed on the far left-hand side to also occur for failure to propagate all the way to the top of this diagram. So when you have these fast, simple, free corrective actions, not only do you address that particular root cause, you perhaps nip a lot of other failure scenarios in the bud just by simply eliminating this entire causal chain on the left-hand side. And so that's very, very, very useful. And so with that, we now have a much more robust design without a lot of time or money being invested. And the more potential root causes we can identify, the more choice we have to solve that problem, which makes it easier and cheaper. And every good root cause analysis, regardless of whether you use fault trees or not, does it in the same way. It starts with understanding our failure event. Now, whether it's Ishikawa diagram, whether it's a fault tree, whether it's anything else, the best way to do root cause analysis is to go down by layers, where you brainstorm one layer down at a time. So you ask your team, okay, this failure event happened. What are the immediate preceding potential events which might have explained this? And you brainstorm all those potential events, and we call that layer one, and you do not move on until all those potential a single layer down causal events have been brainstormed, layer one. And then we focus on one of those, and we again brainstorm for or investigate or identify causal events the next level down. We call that layer two. And if in this case there's only two that we can brainstorm, that's okay. There we pick one of these and go layer three, layer four. We keep going down until we get to an explanation where we believe that explanation, that event, is a root cause, something we can do something about. And we keep going down our other branch, because that's not a root cause yet, and we stop once we identified root causes, things we can do something about. Then we go back up to the next event that hasn't been brainstormed out, go down one layer at a time. Sometimes there's only a single thing we can think of in that causal chain. Next layer down, and we keep going, and we keep going through all these different events, one layer down at a time, which sounds tedious and can be if you have a wrong mindset. But now we have, for example, on the right-hand side, a really simple explanation for this failure. We only go down 2 layers to get to a potential root cause of failure. Now, this is how you get harness that expertise, that experience within your team to get all these 19 potential root causes of failure in order to generate those corrective actions. Now, corrective actions, they exist because we're not supposed to be here to admire problems. We are here to solve problems by finding the vital few corrective actions which are going to save the day. So remember, for our smaller, where we were concerned about solder joint fracture, in that scenario where we are all about where we're trying to get on top of future failure events involving that particular scenario. And let's just say, even though I've given you a scenario, I'll give you some examples of corrective actions for solder joint fracture. Let's look at how a fault tree can take this concept of a failure event to help us get there. Fault trees can really, really help. Now, what is a fault tree? Fault tree looks like this. It's a logic diagram. And the fault tree has at the very top a top undesirable event, which is a round shape. It's not a circle, but it's sort of a rectangle with rounded corners. And again, the fault tree has lots of circles at the bottom called basic events, which are going to be our root causes of failure. These are the events which potentially trigger our causal events. And once we find these circles, which represent these basic events, it makes it very easy to find corrective actions. And one of the reasons I love fault trees during RCA is because they have diamonds, and not because diamonds are expensive, but diamonds represent undeveloped events. They're just events that we think might be relevant, but we're not entirely sure. We don't want to slow down the brainstorming. So I put a diamond in there, and that just tells us we need to come back later on to look at that diamond, that undeveloped event, because we might not have had the expertise in the room, but we can't rule that potential causal chain out. So we're going to put it there. It's important to record our brainstorming, but it means it's a symbol for us to come back and explore later on. Then we have these input events, these rectangles here, which, for lack of a better term, are just labels. They help us label what different parts of our fault trees mean. And then we have these shapes, these weird looking shapes. These are called logic gates, and they represent events that occur when certain combinations of other events occur. In the logic gate on the left is called an OR gate, got a round top and a round bottom, where any of the events or gates below it need to happen for that OR gate to be deemed true or allow an output event to occur. The AND gate is seen as the opposite of the OR gate, where it only is true, or there's only ever an output event, if all the events or gates below need to happen. And a really easy way of understanding the difference between an AND gate and an OR gate is to look at a system like this. This is a 2-pump system, and the system fails only if pump A fails and pump B fails. This is what we call a parallel system because these pumps are arranged parallel. One is redundant to the other, which means that the system will only fail if one pump A fails and pump B fails. And so we can turn the failure of each pump into a basic event represented by a circle, which then can be more easily represented with what we call component identifiers. In this case, the letter A represents pump A, the letter B represents pump B. We can use these basic events to create a really simple fault tree. There's our top event, there's our AND gate. You can see that failure will not occur if only pump A fails, because the AND gate requires all input events to occur. If pump A fails and pump B fails, then we have, unfortunately, our top event occurring thereafter. The AND gate requires all input events to occur, and when it does, in this really simple fault tree, it will then, in a sense, trigger the top event. So an AND gate is great to model parallel systems. Then there is another type of system, which is seen as the opposite of a parallel system. This system requires both pumps to work for the system to work. So the system fails if pump A fails or pump B fails. And this is called a series system because pumps often look like they come one after the other or in series. And so we can turn each pump failure into another basic event to create a fault tree with using component identifiers, letters A and letters B. But the fault tree this time is going to look a little bit different. This fault tree has a top event as per the other one. It also has an OR gate this time because in this case we have a series system we're modeling. And that means if pump B fails, then our system fails. The OR gate is triggered or allows an output event if any input event occurs. And so AND gates and OR gates are often most easily explained when we're trying to model series and parallel system reliability. So let's use fault trees to conduct RCA on solder joint fracture one layer at a time. And so when I'm doing this, when I'm doing a group exercise, which RCA should be, of usually 4 to 8 people, first thing we're going to do is define the top event, the undesirable event. In this case, solder joint fracture, motor cable junction fracture. Now, when we start brainstorming, I say, team, let's brainstorm. I usually ask them to write things down anonymously, and then we share them afterwards. Very good, great way of sort of unleashing the powers of critical thinking and brainstorming. We often start with an OR gate because in this case, we might go to one level down where the motor cable junction fractures due to either overstress or fatigue. These are failure mechanisms. The overstress is a failure mechanism associated with, for example, a single door slam or single shock event, whereas fatigue is all about repeated door closure events where you have a bunch of cycles recurring over time. And you can see straight away that we are already, by having this seemingly minor change or minor difference in explanations, we now set our fault tree up to explore completely different scenarios which might explain what's going on. If we rush to either overstress or we rush to fatigue, then we might furiously fix the wrong problem. Because if we rush to fatigue as the explanation, when the actual root cause is based on overstress, then we are going to not fix a problem at all, even though we think we have. And that's where blame is incurred. Goodwill is lost and money is lost as well. Another potential single level down event is that we used the wrong demonstration test stress. So the test was too harsh, which is a genuine thing to consider. This is all about a potential explanation. Again, we don't want to fix a problem that doesn't exist. Maybe the test was wrong. And the brainstorm finished after that, but we weren't 100% sure that we hadn't missed something. And so the team in this case decided to leave one undeveloped event called other. And this just means or signals that we were able to brainstorm 3 events, possible explanation events, but we weren't convinced they covered every possible explanation. And so we're going to leave this undeveloped event to make sure that anybody else looking at this fault tree in the future is aware we think there's a chance there's more stuff to come. And so the next thing we do is focus on one of these events. And you can see we're using overstress here. This is the input event. We do more brainstorming, excessive shock forces being applied to the joint. That's one brainstormed causal event for overstress. Another one is joints are not strong enough. Why are these explanation events different? Well, the excessive shock forces being applied to the joints mean that there is something wrong with the system around the solder joints. Our solder joints aren't being protected well enough. Whereas if the joints are not strong enough, that means it's the joints themselves that are the issue. Again, we want to make sure we explore everything, because if we rush to conclude that it's the excessive shock forces being applied to the joints, i.e. the system around the solder joints, then all the corrective actions associated with that root cause would be expensive and it might not be relevant. So you need to make sure we brainstorm as many potential explanations as possible to make sure we don't rush to our most obvious or most comfortable or most expensive explanation of what went wrong. And now we keep brainstorming. So now we're going to focus on this input event over here. We believe in this case, there's no more explanation or categories of explanation events. So let's focus on this one over here. We keep brainstorming. Excessive shock forces are being applied to the smart lock. Shock forces being transferred to joints. Now, excessive shock forces being applied to the smart lock, they're external events, whereas opposed to shock forces being transferred to the joints means that the external events are okay, so to speak, but the internal smart lock structure is for whatever reason transferring those shock forces and not protecting the solder joints. And so let's keep going. Those external events, that might sound like, hey, that's an environmental conditions. Well, sometimes we forget about them. Why is that important? Because maybe those excessive shock forces being applied to our smart lock are from drops or bumps during manufacturing. Okay, now this is a circle. This is a round shape because we believe that this is a potential root cause of failure because this is something we control. We manufacture, we build these smart locks. So this is not blaming anybody else. Maybe our own manufacturing process involves excessive drops or bumps. What else? Drops during installation, another potential root cause. So it's got a circle as well. Transportation forces. Now, transportation forces in this brainstorming event, our brainstorming activity, our group didn't think transportation forces was specific enough. So it's another input event, which means we're going to come back to that one and keep investigating. What else did we brainstorm? Substantial door slamming. Hang on. Did we say that we really can't blame the customer or user for substantial door slamming? Well, we'll come back to that one in a minute. And then we have another undeveloped event called other, because in this case, our brainstorming team did some great brainstorming work, but they just weren't 100% confident they came up with every single event on this layer. So those circles represent those basic events, which are going to be root causes we can investigate for further action. Now, the transportation forces, we need to come back to that one because we haven't finished that one yet. And of course, there's door slamming. Now, I like including these basic events, even though at the start of this webinar, I said you really can't blame the customer for too much door slamming, but I like including those basic events and then doing something very visual, like crossing them out to indicate to everyone who's going to look at this fault tree in the future that we did consider that basic event, i.e. customers using it too harshly, but have some explanation as to why it's going to be excluded from further consideration. There's always this, in most organizations, there's always this desire to blame the customers, blame the users. And so if we have the blame basic events in our fault tree and then cross it out or somehow indicate that we're not going to seriously consider it further, it sort of helps channel that rage into more productive interrogation of our fault tree. We don't want someone to say, hey, you didn't even think about the customers or users abusing our door. Well, we clearly did. We crossed it out with an explanation, hopefully, to explain why we did consider it and said this is not going to be something we're going to consider further. And so if we keep doing this approach for our fault tree, we now have these, we can essentially develop a fault tree which looks like this, which has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 basic events. If we exclude the 19th excessive door slamming, we have 1, 2, 3, 4, 5 undeveloped events, which means that if these basic events don't cut the mustard, if these don't explain, or if we rectify these basic events or these root causes and we still have problems, at least we know which part of our fault tree we need to come back to later on. Now, this is not a root cause analysis webinar. This is about how fault trees can help root cause analyses, because root cause analyses would take something like this and then work out which of these basic events are the most likely. And if they're the most likely ones, if you can think of some fast, simple, free corrective actions, you implement those corrective actions. If those most likely basic events don't have fast, simple, free corrective actions, then you might be motivated to do some targeted investigation to see if we can include or exclude those basic events or root causes from further consideration. Because if we can exclude that potential root cause from this explanation of failure, that means we don't have to implement an expensive corrective action. Now, like I said earlier in this webinar, we don't want to be lawyers. This is not about blame. This is not about working out who stuffed up. This might be a scenario where one member of our organization stuffed up by getting the whole solder joint design wrong. But the cheapest way to overcome that problem might be a whole of organization approach where everyone does their own little corrective action, and those little corrective actions might have a collective impact to where the stress that our solder joints experience is drastically reduced. And even though we should blame the person who got those solder joint designs wrong, if we have a whole of organization approach where one just does something very, very small, perhaps, and those small corrective actions, those small responses add up in a way that solve the problem, that means you have an organization focused on reliability and not blame or apportioning responsibility. Now, me personally, I tend to prefer to use fault trees for RCA. The other approach, which I think is just as good philosophically, is the Ishikawa diagram or the fishbone diagram, because the fault trees and the Ishikawa diagrams are the only ones that really allow you to explore lots of different causal events, lots of different basic events on those layers as we go down. The 5 whys and a few other approaches, they simply rush to maybe one, at best 3 potential explanations of failure. And as you can see for our smart lock solder joint, that fault tree came up with 18. So I like Ishikawa diagrams. I'm not going to go into them in great detail in this webinar. There's plenty of resources out there. Maybe another webinar in the future I should be on the Ishikawa diagram. But I tend to prefer to use fault trees for RCA without saying that fault trees are better than Ishikawa diagrams. I think they're both equally powerful. The reason why I like to use fault trees is because I find it much easier to manipulate on a whiteboard when I'm facilitating root cause analysis session. And you can have those sticky notes where we can easily move those events around when we realize we've made a mistake or we've forgotten something or we need to include something more. And so once we realize we need to include something more, the sticky notes are relatively easy to pick up and move around, and you don't need proprietary software to do that. The other reason I like using fault trees is when I'm doing virtual root cause analysis facilitation, it's so much easier to do fault trees on collaborative software. It's still easy to update and adjust because instead of having sticky notes, we have shapes. And with online root cause analyses, where participants are not co-located, they can easily add their own. Often I use PowerPoint, for example, where every participant gets his or own slide where they can essentially brainstorm away. I share the top slide, which is the fault tree itself, and we start building with all the brainstorming that's going on. So I personally like to use fault trees because that fits with my approach for doing root cause analysis. Like I said, fault trees and Ishikawa diagrams are both the best of the best when it comes to RCA, and everything else is a compromise. But I prefer fault trees for that reason. Now, I believe has answered a few of your questions, Carl. I use fault trees. I use a few other things. When it comes to Carl asked the question, is special software need to conduct fault tree analysis? Now, software can be used when you're using a fault tree to conduct system reliability analysis. Like, for example, if you're trying to work out the reliability of those parallel and series systems, you can use software. There are equations you can also use. Many of my courses teach you those equations, but when it comes to RCA, as a rule, we're not interested in quantitative analysis of the likelihood of the top event, I should say. We're more interested in trying to find those potential root causes to then come up with a fleet of great ideas for corrective actions, choose the fast, simple, free ones. You might only ever get to a point where you can narrow it down to 5 likely potential root causes, which means that you have corrective actions which target all 5, and that should hopefully make the problem go away, etc., etc., etc. Well, I lost my train of thought. Yeah, I was just trying to go back to the concept of us not being lawyers when we do RCAs. Too many engineers I find feel like you can never finish an RCA until you found the one true root cause demonstrated beyond any level of any doubt. That's not useful. If you have 19 potential root causes and you can narrow it down to 5, maybe the right thing to do is to implement corrective actions for those remaining 5 explanations, because the amount of time and effort that it would take to verify which one of those root causes was the one is going to be drastically outweighed from addressing all 5 remaining potential root causes now. I also talked about FMEAs. Now, FMEAs, to be honest, FMEAs and fault trees, philosophically, I don't care what anybody says, aren't that different. FMEAs, people will say, are bottom up as opposed to fault trees, which are top down. I've never been part of an enjoyable FMEA experience where it is genuinely bottom up, where you try and think of every single explanation that could result in failure, and then propagate those to all the different top events you can think of. That's been a terrible experience and when people try and do that in the real world, most FMEAs, when they're facilitated well, are actually top down, where you start with requirements analysis and functional failure modes, and then you keep working down, focusing on those the prioritized functional failure modes. So I don't think they are as fault trees and FMEAs are as widely divergent as many of us would have others believe. They are very, very different, and FMEAs are a lot more structured and are way more capable at dealing with lots of different potential top events. But I've done FMEAs or facilitated FMEAs where we use fault trees to help us get to potential root causes. Okay, Jacob, thanks for that feedback. I think I've touched base on most of the questions Carl has thrown my way. You can see that, Carl, you talk about the Kano analysis. Kano analysis, yeah, that's I won't touch base on that too much, but I also use fault trees, like in my fault tree analysis course. Talk about robust customer-centric design, which is analogous to some of the concepts that Kano analysis touches on. But I won't go into it in too much detail here. Essentially, we use fault trees to work out which things are most likely going to frustrate your customers the most. Very powerful, but a different application. Okay, I think we're almost at time, but are there any questions? Samantha asks, how long should a fault tree exercise take in an organization? Great question, and I can't give you a straight answer. So, for example, fault tree analysis was used by the Columbia Accident Investigation Board that NASA conducted, well, NASA stood up, correction, the US government stood up after the Columbia disaster in 2003. And that fault tree took a long time to essentially help them find the true root causes of failure. If you're having a manufacturing problem, a fault tree could be done within half an hour to help you get to, or even less, 15 minutes perhaps, especially if your people are well trained, know what fault trees are all about, and most importantly, are on board with going down one layer at a time. So if I'm facilitating RCA, then I've had a chance to train the people, or at the very least, people know how important it is to go down one layer at a time. Fault trees can be done very quickly and also very powerfully as well. So I can't give you an exact answer, but 15 minutes for some problems is not out of the question. A couple of years for the Columbia Accident Investigation Board was also somewhat appropriate for the scale of that problem they're trying to understand. Galena asks, when you have too many basic events, how do you decide on the priority of addressing them? Okay, fantastic. Great question. So that's where you need to, so for example, for RCA facilitators, you need to have a plan of attack. And that plan of attack is often going to be based on the likelihood. The severity of the event is what it is. The top event, the failure investigating, there's no, uh, it has cause and effect, which is static for the purpose of this discussion. As a rule, what I tend to do is when we have 19 basic events, I have an anonymous survey with my participants. I say, okay, everyone pick which one you think is the most likely. And that one gets a 10. Right. Okay. So basic event root cause, potential root cause number 3. That's the one I think is the most likely one, the one that's going to most likely explain what's going on. And then I say, okay, then prioritize. So relative to that most likely potential root cause, what do you think the others should be scored as? So if you have another potential root cause which you think is half as likely, it gets a 5. If you have another one which you think is 1/10 as likely, it gets a 1. And then your root cause analysis is not finished until you have essentially chased down those root causes to the point of implementing corrective actions. So for my root cause analysis course, where we focus on the smart lock again with a different failure event, we have a bunch of basic events, but we're able to break them up into basic events which be caused by, for example, humidity from the environment. And that means we are able to say, you know what, if we do an analysis to work out the distribution of these failure events across the scenario I pull is my native Australia. So we have 3 generalized climate regions, one which is very humid, one which is moderately humid, one which is very dry. And if we can find correlation between failures and these different climate groups based on humidity, that's evidence to suggest the root cause is based on environmental humidity, or at least that plays a role. And that often means that we might have defective seals that allow the humidity from the environment to get in. And so it starts essentially allowing us to eliminate basic events after we've categorized them into different bins that can be easily confirmed or discredited based on some investigative analysis after that. Galena, did that come anywhere close to answering your question? Cool. Awesome. Thank you, Kingsley. Thank you, Patricia. Any more questions? So just to clarify, these are great. Thank you, Shashia. These are great questions about RCA in general. Just be aware this, the scope of this webinar was about how fault trees can help RCA. So we've touched on how it can help RCA, touched on some RCA things, but this is not an RCA webinar. So if you want to do RCA, now that you've been energized to use fault trees, don't forget to keep learning about some good techniques. Galina asks, can you connect FTAs to FAMIRs? Yes, you can. There's, like I said, when I facilitate FAMIRs and we have a genuinely perplexing scenario, we have a system functional failure mode, which we think's likely or think's relevant. We're not really on top of the root causes behind it. We might break out an impromptu fault tree analysis within the FAMIR itself, come up with root cause analyses. I guess, Galena, could be wrong. I guess you're talking about a fault tree analysis which has been done beforehand. You can actually take, if the top event, for example, was a system functional failure mode, such as smart lock takes too long to unlock. So let's just say you've done a fault tree for that. Well, most of those events, input events and basic events, you can actually take and put them in a FAMIR if you need to for whatever reason, because essentially a FAMIR is all about brainstorming system functional failure modes and their potential root causes. Is that what you're talking about, Galina? Cool. Yeah. So don't let anybody tell you that FTAs or fault tree analyses and FMEAs, they're like water and oil, they can never be mixed. No, you use whatever technique you want to use to help you make the best decisions. If you want to create your own fault tree for me, a hybrid activity, as long as it helps your team get to potential root causes of failure, you go for it. And there's no reason why the two cannot be mixed, even though textbooks make it seem like one is the opposite activity to the other. Like some textbooks say they are the opposite activities. No, they're all about you have an undesirable event, real or potential, and you're trying to find root causes. And yes, for me, is all about finding the potential root causes for way more than one single basic, single top event. But at the end of the day, it's all about trying to make things more reliable. And of course, fault trees can also be used for system reliability analysis, which is an entirely different subject I won't cover on too much today. Any more questions? I think I've got a few from Carl on the Q&A. So, Swiss cheese models commonly used to guide root cause analyses, RCAs, and safety efforts across a variety of industries, including healthcare. Various safety and RCA frameworks to find the holes in these cheese and their relationships have been developed, such as human factors analysis, classification systems, etc., etc., etc. Swiss cheese and its associated tools are intended to help safety professionals identify holes in each layer of cheese or level of the system that could or did lead to an adverse event, so they can be addressed, mitigated before causing harm in the future. Any thoughts? My thoughts is as a rule, I see Swiss cheese things as pretty little pictures of cheese, the start of reports to explain the concept of how layers of protection can have holes. If those holes line up, bad things happen. As a rule, beyond that basic level of eye candy for a report where the Swiss cheese picture is included, I don't see the subsequent reports or subsequent content in the reports actually genuinely adhering to the concepts embedded within Swiss cheese analysis. I just see it as a very people feel it as it's a very useful sort of visual aid. So I don't see Swiss cheese analysis as a rule as prevalent as number of Swiss cheese images in reports for RCAs. That's my thoughts. Another thing you ask is RCA is a cybersecurity method teams use to get to the heart of a data breach, cybersecurity incident. Cyber attack occurs, the SecOps team must come together, as the name suggests, to find the root cause of the problem by conducting an analysis. Any thoughts? My thoughts are that fault tree analyses could be used by, and have been used by SecOps teams in the past to great effect. I think I've touched on the Kano models, which talk about what's called customer happiness and usability and things like that. So hopefully that covers off on that. And thank you for the feedback about it being a good presentation, Carl.